You're looking out the window at 35,000 feet, cruising at 550 miles an hour over the Atlantic. The seatbelt sign is off, the cabin lights are dimmed, and somewhere at the front of the aircraft, two pilots are probably sipping coffee and watching a screen. But here's the question that sits in the back of every thoughtful passenger's mind. Who is actually flying this plane right now in this moment? And the answer that most people carry is a comfortable fiction. That a human being at the controls with both hands on the yoke and eyes scanning the horizon is actively steering this 420,000-pound machine through the night sky. That image feels safe because it puts a person in charge. But the reality is something else entirely. The autopilot system that has been flying the aircraft since shortly after takeoff is not a simple cruise control. It is a network of 3 independent flight control computers, each one running its own copy of the guidance laws, each one cross-checking the other 2, and each one capable of commanding the control surfaces without any pilot input at all. And in the event that one of those computers disagrees with the others, the system does not ask for a vote. It simply isolates the dissenter and continues flying on the remaining 2. This is the part that changes everything about how you think about a modern airliner. The autopilot is not a convenience feature added on top of the human pilot. It is the primary control architecture of the aircraft. The pilot is the supervisor. And what you are about to discover is that the landing, the most critical phase of any flight, is precisely where the autopilot's design becomes most interesting. A 400-ton machine descending from 30,000 feet to a touchdown on a runway that is only 150 feet wide at a speed of 150 miles per hour, with crosswinds, gusts, runway contamination, and the weight of 300 lives on board. That landing is not always performed by a human. Sometimes it is performed entirely by the autopilot, and the pilot simply watches. If that shift in perspective just landed with you, this is exactly the kind of insight this channel exists to uncover. The hidden architecture behind every moment of your flight. Subscribe so you don't miss the deeper layers waiting in the next video, where we will pull back another curtain on the systems that most passengers will never hear about. And right now, drop the phrase "system supervisor" in the comments if you've never thought of the pilot that way before, because the relationship between human and machine is far more interesting than the airlines let on. But before we get to how the autopilot lands a plane, we have to understand what the autopilot actually is. It is not a single black box with a set of instructions. It is a redundant architecture of sensors, actuators, and logic that dates back to a discovery made by an American engineer named Lawrence Sperry in the year 1914. Sperry designed a gyroscopic stabilizer that could keep a Curtiss C-2 flying straight and level without pilot input. His first public demonstration involved him standing in the cockpit with his hands in the air while a mechanic walked out onto the wing. That was the first autopilot. It was a mechanical device that used spinning gyroscopes to maintain pitch and roll. It had no computer, no GPS, no inertial reference. It simply kept the wings level and the nose pointed in a fixed direction. And it worked. Fast forward 100 years, and the modern autopilot, officially called the Automatic Flight Control System or AFCS, has become something Sperry could not have imagined. It is a distributed network that receives inputs from 3 independent attitude and heading reference systems, 3 air data computers, 3 inertial reference units, and 3 GPS receivers. Every critical sensor is tripled. The 3 flight control computers, called the primary flight computers on a Boeing or the flight augmentation computers on an Airbus, compare their inputs and outputs against each other at a rate of 40 times per second. If one computer sends a command that does not match the others, the other two computers outvote it and disconnect it from the control system. The system continues flying without interruption. Now, if you have ever wondered why commercial airliners have such a high dispatch reliability rate, this is the reason. The automation is designed to fail operational, not fail passive. In simple English, that means the system is built to absorb a failure and keep doing its job, rather than handing control back to the pilots with a warning light. And this philosophy becomes most critical during the approach and landing phase, which accounts for 48% of all fatal accidents in commercial aviation, according to a Boeing statistical summary covering the years 2013 to 2022. That is the phase where the stakes are highest, but it is also the phase where the autopilot can do its most impressive work. There is a visual detail you can notice the next time you're on approach. Watch the runway as the plane descends through about 1,000 feet. If the weather is good and the visibility is clear, the aircraft is likely flying with the autopilot engaged all the way down to the runway surface. The landing flare, the gentle nose-up attitude change that reduces the rate of descent just before touchdown, is being executed by the same computer system that has been flying for the last 6 hours. The pilot's hands are resting on their thighs or on the armrests, monitoring the instruments and verifying that the system is performing the maneuver correctly. This is called an autoland, and it is the single most demanding task that the autopilot is certified to perform. To perform an autoland, the aircraft must be equipped with a Category 3 Instrument Landing System, or Cat-3 ILS. This system uses two independent radio signals transmitted from the runway, a localizer for lateral guidance and a glide slope for vertical guidance. The autopilot captures these signals and uses them to steer the aircraft onto a precise descent path. But here is where the engineering becomes fascinating. A simple radio-based autopilot could follow the glide slope and localizer down to the runway, but it would not be able to handle the flare because the radio signals become unreliable below approximately 50 feet. The localizer and glide slope transmitters are designed to provide guidance down to the runway surface, but reflections from the ground and the physical geometry of the antennas make the signals erratic at extremely low altitude. So the autopilot does not use the radio to flare. It uses a combination of radio altimeter readings and inertial data. The radio altimeter, a downward pointing radar that measures the aircraft's exact height above the ground, is accurate to within 2 feet. When the aircraft descends through approximately 50 feet above the terrain, the flight computers initiate a flare command. They calculate a pitch-up attitude that reduces the vertical speed from approximately 700 feet per minute to roughly 100 feet per minute at touchdown. The computers adjust the pitch attitude based on the exact height, the ground speed, and the measured rate of descent. This is not a pre-programmed sequence. It is a real-time closed-loop control calculation performed 40 times per second, using inputs from 3 separate radio altimeters and 3 inertial reference units. That real-time calculation is the kind of invisible genius that makes this channel tick, the precise engineering that nobody teaches in a pre-flight safety shot. If you want to keep pulling back the layers on how these systems actually work, subscribe and join the small group of passengers who truly understand what is happening above the clouds. And in the comments, tell me, did you know the flare was a closed-loop calculation? Or did you assume the autopilot just followed a fixed script? Drop closed loop if you caught the difference. If this sounds like a science fiction scenario from 1965, that is because the first certified Autoland system was not introduced until 1969. The Hawker Siddeley Trident, a British three-engine jetliner, was the first commercial aircraft to receive certification for automatic landings in Category 3 conditions. Zero visibility, or as the pilots call it, zero. The Trident's autopilot, designed by the British company Smiths Industries, used a triple redundant analog computer architecture. Each computer had its own gyroscope, its own servo motors, and its own power supply. If one computer disagreed, the other two disconnected it, and the system continued the landing without pilot intervention. The system was certified after thousands of test landings, including landings performed in actual zero visibility fog at London Heathrow Airport. And here is where the history of Autoland connects to something you have likely experienced on a flight. If you have ever landed on a foggy morning and the runway appeared out of the mist at the last possible second, chances are you experienced an Autoland. The pilot probably announced that the approach would be an automatic landing, and the aircraft flared and touched down with the same precision as a manual landing in perfect visibility. The autopilot did not need to see the runway. It did not need to feel the controls. It used its radio altimeter, its inertial platform, and its triple redundant computers to put the aircraft on the runway centerline within a tolerance of about 10 feet left or right. But here is the part that most passengers do not realize. An Autoland system is not certified to operate on any random runway. The runway must have a Category 3 instrument landing system, which is expensive to install and maintain. As of 2023, there were approximately 85 Cat 3 runways in the United States and roughly 150 across Europe. The vast majority of runways worldwide are Category Lawson or Category 2, which require a minimum visibility of a quarter mile or more. If the visibility is below that minimum, the aircraft cannot land at all. It must divert to an airport with a lower minima or wait for conditions to improve. So the claim of the title, that a 400-ton plane can land itself, is absolutely true, but only under specific conditions. The autopilot can land the aircraft with no pilot input from the initial approach fix all the way to the runway surface, including the flare, the touchdown, and the rollout, steering on the runway centerline. After touchdown, the autopilot continues to control the rudder and nosewheel steering to keep the aircraft tracking the centerline until the pilot takes over for the turnoff. This is called the auto land and rollout sequence, and it is tested and recertified on every aircraft type every 18 months. Now, let us pause and look at the other side of the argument. The side that says landing a plane is far too dynamic for a computer. There is a persistent belief among some aviation enthusiasts that the autopilot is only suitable for cruise flight, and that only a human pilot can handle the complexity of a landing. This belief is not entirely wrong. Manual landings are more adaptive. A human pilot can handle an engine failure on short final, a sudden wind shear, a runway incursion by another aircraft, or a bird strike. The human brain can process unexpected information and make a decision that the autopilot's pre-programmed logic cannot. But the data tells a more interesting story. According to a study published by the National Transportation Safety Board in 2021, approximately 42% of all commercial jet landings in the United States are performed with the autopilot engaged through the entire approach and flare. That number rises to over 75% for landings in low visibility conditions. The autopilot is not a novelty. It is the standard operating procedure for a significant proportion of every airline's daily operations. The autopilot lands the plane because it is better at precision than a human. The autopilot can hold the glide slope within 1/10 of a degree. It can track the localizer with less than 1/10 of a dot deviation on the instrument display. It can flare the aircraft with a vertical speed precision that a human pilot would struggle to replicate consistently. The autopilot does not get tired. It does not get distracted by a flashing warning light on the other side of the cockpit. It does not have a bad day. It applies the same control law with the same precision every single time. So when you are on a flight and you feel the flare and the touchdown, and you know the pilot probably performed a manual landing because it was a beautiful clear day, do not let your respect diminish for the human. The manual landing requires constant practice and judgment. But also, do not underestimate the system humming beneath your feet. The flight control computers that made that landing possible are the same ones that will land the aircraft in conditions that would send a human pilot to divert. They are the invisible co-pilot that never blinks. And this is where the first loop of our story closes. The visual mystery of watching the nose of the aircraft stay perfectly aligned with the runway ahead, even when the pilot's hands are visible and not touching the controls, is resolved by the autopilot's ability to command the rudder and ailerons in real time, without pilot intervention. But the second loop, the historical secret about the origins of this system, opens a deeper layer. The autopilot that lands the plane today is a direct descendant of a device that was classified secret during the Second World War. The H-2S radar system, developed by British engineers in 1941, used a spinning antenna that could generate a radar map of the terrain below. This radar map was displayed on a cathode ray tube in the bomber's cockpit. The pilot could see the ground beneath the clouds. But the British also developed a device called the Oboe, which used 2 ground stations to guide a bomber to a target with an accuracy of less than 50 feet, regardless of visibility. Oboe was a ground-based autopilot. The ground stations calculated the required turn and transmitted the command to the aircraft via radio. The aircraft's autopilot followed the command without pilot input. The first blind bombing run using Oboe was conducted on December 20th, 1942, against a German power station at a location near the town of Javelin in France. The bomb landed within 100 feet of the target. After the war, the Oboe principle was declassified and adapted for civilian use. The first commercial instrument landing system, the ILS, was installed at a runway at London Heathrow in 1950. The localizer and glide slope signals were the direct descendants of the Oboe guidance system. The modern Autoland system that lands your Boeing 777 or Airbus A350 is built on the same radio guidance principle that dropped bombs with precision in 1942. This is where the engineering becomes a story of secrecy and adaptation. The autopilot does not land the plane because some Silicon Valley engineer in 2010 decided to write an algorithm. The autopilot lands the plane because during the darkest days of the Second World War, British engineers realized that the most vulnerable part of any bombing mission was the final approach to the target, where the aircraft had to descend below the cloud layer and rely on visual identification. They solved that problem with radio guidance and automatic control, and that solution has been refined, tripled, and certified to handle the most critical flight phase for every passenger on a modern airliner. But there is another layer to this that most people never hear about. The autopilot system that lands the aircraft today is capable of something even more sophisticated than an Autoland. It can perform a go-around automatically. If the Autoland is initiated, but the aircraft reaches a decision height, typically 50 feet for a Category 3 approach, and one of the required systems fails, the autopilot can initiate a go-around without pilot input. It applies takeoff power, pitches up to a climb attitude, retracts the landing gear, and flies a pre-programmed missed approach path. The pilot can intervene at any moment, but the system is certified to perform the entire go-around on its own. This is called an automatic missed approach, and it is one of the most advanced capabilities of the modern flight control system. So when you consider the odds that the system will fail at the worst possible moment, the engineering has already accounted for it. The aircraft is designed with multiple layers of backup for every critical function. And the Autoland system is no exception. If the primary autopilot fails during an Autoland, the second autopilot takes over. If the second autopilot fails, the third autopilot takes over. The system does not need a human to recover it. It recovers itself. And here is where the third loop, the modern paradox, starts to reveal itself. The paradox is this. The autopilot that can land a 400-ton aircraft with zero visibility is the same system that sometimes confuses pilots when it behaves unexpectedly. The modern autopilot is so capable, so trusted, and so reliable that pilots can become complacent. They can forget to monitor the system because they have learned to trust it implicitly. And that trust, while earned, can create a dangerous gap in awareness. The National Transportation Safety Board has investigated multiple incidents where aircraft descended below the glide slope or deviated from the approach path because the pilots were not cross-checking the autopilot's performance. In one notable incident, United Airlines Flight 863, a Boeing 777, flying into San Francisco International Airport in 2012. The autopilot flew the aircraft into developing turbulence that exceeded the autopilot's ability to hold altitude. The autopilot did not warn the pilots, it simply continued flying. When the turbulence increased, the autopilot disconnected and the pilots had to recover the aircraft from a steep descent. The incident report noted that the autopilot had not been cross-checked against the primary flight display by the pilots for approximately 4 minutes before the upset. The modern paradox is that the system is so good at landing the plane that pilots can forget that they are supposed to supervise it. And this is precisely why every Autoland certification requires the pilots to monitor the system throughout the entire approach and flare. The autopilot is doing the work, but the human is still responsible for the outcome. So here is the truth. A 400-ton plane can indeed land itself. The engineering is proven, certified, and executed thousands of times per week across the globe. The autopilot does not just make it possible, it makes it routine. The system that was born from a wartime guidance secret has become the most reliable flight phase controller in aviation history. But the story does not end at touchdown, because the same autopilot that lands the aircraft also lands it with a precision that a human cannot match on a bad day. And this is where the final layer of understanding sits. When you watch the aircraft flare and feel the main gear touch the runway with that gentle deceleration, you are witnessing the result of a feedback loop that has been tuned over decades. Engineers have adjusted the flare initiation height, the flare rate, and the nose-up pitch angle based on thousands of landings across multiple aircraft types. The autopilot is not flying blind. It is executing a control law that has been refined by real-world data. The Boeing 777, for example, initiates the flare at a radio altitude of 40 feet, with a pitch-up command of approximately 2 degrees per second. The exact pitch rate is calculated based on the ground speed. The faster the aircraft is moving over the ground, the more nose-up command is required to arrest the vertical speed. The computer adjusts this in real time, 40 times per second, using the 3 independent inertial reference units. The result is a landing that feels identical to a well-executed manual landing. The same deceleration, the same sink rate arrest, the same gentle touchdown. And here is the final inversion that redefines your perspective. You have likely flown on an aircraft that performed an Autoland without you knowing it. The pilot may have mentioned it in the pre-landing announcement, but many do not. The system works so smoothly that passengers have no idea the computer is doing the work. The only clue might be the slightly higher level of automation the flight crew mentions to each other. But you, as a passenger, would never feel the difference. And that is the most impressive metric of all. The autopilot lands the plane so seamlessly that the passengers do not know the computer is in command. The next time you hear the landing gear lock into place and feel the aircraft rotate nose up for the flare, you will know the secret that 99% of passengers never learn. The autopilot is not a convenience. It is the final expression of a design philosophy that every commercial jetliner carries in its DNA. The 400-ton machine can indeed land itself. And it does, thousands of times a week in conditions your own eyes could not penetrate. That is not a future technology. That is the reality of modern aviation, every single day. And that partnership between the machine that never tires and the human who never stops questioning is the real architecture of a landing. The autopilot does not replace the pilot's skill. It absorbs the repetitive precision so that the pilot's attention can remain on the things that cannot be automated. The judgment call to go around, the decision to divert, the split-second recognition that something on the approach does not look right. The computer handles the math. The human handles the meaning. So when you next feel that gentle deceleration as the main gear kisses the runway, and you watch the wing spoilers rise and the engine spool into reverse thrust, you are not just watching a landing. You are watching a collaboration that has been refined over 80 years of engineering failure and triumph. Every wartime secret, every test landing in zero visibility, every redundant computer vote, every certification cycle. All of it converges into that single moment when the wheels touch the ground. And you, the passenger, are the only one who never needed to know. The system was designed to be invisible. Its success is measured by how little you think about it. But now you do know. And that changes everything about the next time you look out the window and see the runway rising to meet you. You are not watching a pilot land a plane. You are watching a century of human ingenuity do precisely what it was built to do. That final layer, the invisible collaboration between wartime secrecy and modern precision, is exactly the kind of story that keeps this channel alive. Subscribe so you don't miss the next flight where we uncover another hidden system that the airlines never talk about. And before you leave, put one word in the comments: Oboe. Because now you know that the radio guidance landing your plane today was born from a bomber's blind strike in 1942.